does something faster.
That's pretty cool.
You create that.
You have to like use it, or you just have to
It's called partial reconfiguration, and it is supported by certain things. I don't think it's like a universal thing. It's like hardware specific how it gets done.
Huh? 40, I finished 8. That's what it's important.
Class doesn't feel like it.
Someone doesn't want it.
I feel like class doesn't feel like it.
But
Yeah, I'm surprised.
it's like
People are so awake.
But I'll be full now, right?
Yeah, I feel like this
Yeah, the patient
for an 8 a.m. Everyone's
What class did you take?
Yeah.
It's basically there's so many elements.
No, it's protein.
Like I like it when he makes fun of me. I like that. He
Oh,
does.
Yes, that's why he does it.
And I'm also okay with it.
So basically, machine learning.
I'm just surprised by how much other people
supervised and trained for engineering development, right? So you just see
Ryan on the same Adam behind.
So what he suggests
I don't know anybody
is
else,
that
but
take
that was
Xinjiang
Someone behind me.
course so that he's taking
I don't even know who Adam
so
is.
it's
I
like
just looked around and was like, I don't know who or what, who said anything, but
Yeah,
I just thought
I have hope for your last section.
Yeah.
But we'll see once the assignments start up.
Yes.
How many sections?
Emma,
Just
that
one.
you go tell him
Yeah. But I'm saying like this.
Yeah,
Go
just
year.
yeah. Well, that sounds. Well, I figured out how to do Todd's assignments on Windows. I was helping Rachel out.
Oh,
How long did that take you?
I did it during class.
Windows suck.
Did you use a Unix box of any kind? Or
Yeah.
you set it up straight?
You did use WSL.
Okay.
I did the WSL. It took like 15 minutes to set up.
Oh, really? Yeah. I did it, so after I figured out how to set it up, it took like 5 minutes.
Yeah.
You just do, you have to download Git Bash.
Yep. Oh, did Rachel not use the badge to this?
Oh, that's sweet. We've never had to use it.
Oh.
Had
Oh, okay.
And then, of course, VS Code. I had her download
Nice, no?
GitHub Desktop, which turns out she
Oh,
doesn't need it.
it's so useful for actually.
Yeah. No,
No,
because
no.
I can't do a Git push on
That's for
mine because
generation
I was
2.
too lazy to
Generation
figure
2
out a second
doesn't
key.
support this for
But
like-
Rachel can do it perfectly on her computer. I was like, bruh.
You're still
Like through Git Bash, apparently it can just bypass that whatever security.
I mean, I'm sure you generated as permissions.
Yeah, but 2017.
Oh.
That works perfectly.
So I always go to that
down.
page where it's like, how to do your Git key.
Yeah. How to generate and how to add. I just have those say.
Anyways, but
But yeah, no, every time I have to look it up.
I feel like it's not important enough to constantly.
no. You already got
where I
3 days
probably
before.
should have wrote a script, like
Just to do
a
it.
while back ago.
No.
That's just like auto-generate a key. Go to
Yeah.
GitHub settings and then pull up, paste it.
Yeah.
Exactly, we don't know.
Auto generate and copy it to my clipboard.
Yeah, that's why I spent a lot of time programming degrees to pick it up on my laptop because I had it on my desktop.
Yeah, what Windows? Yeah. WSL wasn't working. So I gave up on that. I gave up on that solution very quickly.
You know, on Windows I use WSL for most general stuff and then Git Bash specifically only for Git.
Yeah, it was weird. Rituals WSL is
It's always-
installed and downloaded. It just doesn't do
It's
what I
always
wanted to.
broken.
Yeah. I was like, okay, I'm giving up with anything Python related when going through
The
WSL.
longest trouble I've had difficulties just installing anything, like with the sudo apt command.
Oh, yeah.
But I think I fixed it because I was able to install Python because the script uses 3.11 stuff.
It's like for this before the USL, it's like a 100% emulator.
Oh,
That's what I should. From using WSL so much, I probably should look at that.
Yes.
Or more complicated stuff. But yeah, because WSL is pretty okay-ish enough for an alternative. But
If you use Docker in it, it will follow the command.
that is why I don't
That
use
sounds about
Docker.
right.
Yeah. But it's also like there's been so many of those. I'm like, can I just take this like a Linux laptop.
Huh?
Oh,
'Cause, like,
Rachel's done that. Rachel's done a boot camp.
I know. One of my friends is.
So now I'm like at professional. I'm like,
I'm
okay,
studying
whenever I have the time, I
Linux.
have to sit down, and this is just a Linux machine, and just go through the
He's
ISO.
Same age as you. So basically, you know,
Probably
you
have to
need
do
three
it
times.
Yeah.
because
No,
it's a
you have to.
Microsoft computer.
Yeah, you did medical, but you did.
Well, Rachel has a
was in
Lenovo
chemical.
Yeah, like this is it's specifically like Microsoft thing, so I'm almost certain they're not gonna let me like easily.
Yeah.
You just wipe it. If you have a boot drive,
Yeah.
you just wipe the Windows.
That's true.
If you wanted to completely switch it over.
Yeah. Which, knowing me, I'd probably do just dual boot just in case
Yeah.
I can't figure something out in Linux, and it's like
Yeah.
not as.
Or if you want it ever installed.
Yeah, that's true. Like,
Unless it's a school computer,
Mhm.
I'm pretty sure you should be able to turn off secure boot and any other window.
Yeah, exactly.
Either through them or
yeah. Because, you know, like, finally it's just like, what if they require, you know, Windows only software?
Yeah.
Yeah, that's good.
Probably when it does. I'm getting to the point where, like, for school, I shouldn't really take the job.
Audio.
Because all this is annoying. And I don't wanna buy a Mac.
Yeah, that's what.
Fair.
How is class going?
That doesn't sound that fun. Somehow that sounds so lame.
last project, and like I was very worried because my partner had
Nice. Fair.
he wrote a lot of it, that's fine.
But yeah, I'm not having the debugger.
I have that.
Okay, very nice. People. Questions from last meeting? Anything?
I have a curiosity that I don't want to derail things later. Is like parallelizing a for loop constant? Like, does it remove n terms? So say like you have a for loop that goes n times, and you parallelize it on n cores. Does that make it like constant for setting up the parallelization? Or
If they're really independent of each other, yeah,
Okay.
definitely. And if the access to memory is friendly to it, and it starts to be an issue, usually it's not a big deal if you want to read from the memory, but if you want to start writing for the memory, then you run into concurrency issues, so they might hold one until the other one stops writing. But in general, yes. Okay, let's go very quickly over a few examples of running time, and then talk about randomized algorithms. And we're going to speak a lot about QuickSort, not because I don't think that you know QuickSort, but because I know, or assume that you all know QuickSort, but there is a lot of ideas to study from QuickSort that then will form other algorithms. So that's why QuickSort is such a big obsession. Start from this example that hopefully you all checked at home, that is recursively call itself with parameters n, print n asterisk, call itself with non-int n minus 1, and you have an example of a recursion formula, t of n equal t of n minus 1, the running time of n items, plus a constant. What is this constant? We don't know, we don't care. It's something that depends on how fast our computer needs to print one such constant, evaluate the ifs, and so on. And there are a few ways that you've seen to solve such recursion formulas. If you don't know anything, then you just start substitute. What is t of n? It's just, what is t of n minus 1? It's just c plus t of n minus 2. What is t of n minus 2? It's just c plus t of n minus 3, and so on. And when you're looking at this formula at the end of the day, you are getting that you printed n minus 1 such stars plus a constant time. So altogether it's linear in n. Nothing much to say about it. If you have seen the master theorem before, it's fine to use it. I'm not a big fan, but it is a technique. It's a big hammer that can solve such cases. Slightly different formula. Now it's no need of n minus 1. Now, did you change something? No, I did not. No. Now, instead of printing 1 star, I print n stars. So the overall running time is print n stars, n asterisk, plus t of n minus 1, which is print n star plus print n minus 1 stars plus t of n minus 2, which is keep repeating such iteration over it, and you're getting that the total number of stars or constant times, you're spending a constant time per each item in this loop. You just use a star, the asterisk, as you have to spend a constant time to print it, to evaluate if you need any more or not. All in all, you're getting to, after n steps, you're getting to the following formula. It takes constant times n plus n minus 1 plus n minus 2 plus n minus 3 all the way till 1, plus till t of 1, which is a constant. Reading the same formula, the same sum, but now from right to left, it's just 1 plus 2 plus 3 all the way to n, which is just the arithmetic sum that we saw last time. N times n minus 1 half. So all in all, it takes linear time. Arithmetic sum at this point, everybody should be expert at. Okay, with n, as long as k is smaller than 1, do k equals 2 times k. We'll start with k equal 1, then k will be 2, 4, 8, 12, and so on. So, 2, 4, 8, 16, and so on. So how many iterations could we have? Well, let's ask what is the value of k after I iteration. After I iteration, k equals 2 to the I. After I iteration, k equals 2 to the I. So how many iterations could I have before 2 to the I becomes larger than n? How many iterations could I have such that 2 to the j is still smaller than n? And the answer is, of course, log 2 of n many iterations. Plus 1, minus 1, depending if you're asking how many iterations do I have, including the one unsuccessful where I look at the while but decide that k is too large, or just successful one where k is still smaller than n. Okay. Do it either way. And how do we write it? We write it as the number of iteration is log to the base 2 of n, but since log to the base 2, if I want to move from one log to another log, I just need to multiply by this constant log to the a of b. Then when I write the log, I don't care about the big O. If I'm going too fast, it's material that I always teach at the beginning of grad or undergrad algorithm. Usually I'm going much slower, find the videos of me teaching. Elsewhere, and I have more time to go for it. Here I'm trying to get to the cool stuff of the course a bit faster. Okay, that's an example that closer to other things that we'll discuss today. Very cool example to my taste. So we are reading a value n. For I goes from 1 to n I plus plus, and for j goes from 1 to n. Do j equal j plus I. Now, if I write the j equal j plus I by j equal j plus 1, then obviously this whole thing takes n squared time. But this one n's time, and this guy once, well, not exactly n time, but 1 plus 2 plus 3 plus 4 plus all the way up to n. So it would be n squared just because of the arithmetic sum. But here it's something a bit more subtle. So is it true to say that it's order of n squared? Yes, for the same exercise. So last time, it's order of n squared legally. It's not more than n squared, because if I may replace it by something slower, it's still n squared. But the question here is it actually theta of n squared, or can we find a better running time? And a little hint here is this picture out there that show a string, like a guitar string, and in the string you see the harmonics. You see that you can have one wave, one standing wave, whose length is the length of the whole string divided by 2, and one that is divided by 3, and one that is divided by 4 and 5, and all these different harmonies that you see in the whole string. How is this all related to this problem? Well, let's see. When I is 1, then the inner loop goes through the values j equal 1 to 3 dot 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 all the way up to n, and j increments when I is 1. J is incremented by 1 at each step. So how many stars do I print when I equals 1? It will be n many stars. What happens when I equal 2? Slightly more interesting. J will start from 2, then j equal j plus I, 4, 6, 8, all the way up to n. But how many numbers do I have which are even between 1 and n? Well, floor and ceiling, but we don't have any respective. Floor and ceiling, we just ignore it. So it's n half. Floor, ceiling, many stars are printed when I is 2. What happens when I is 3? J will start at 3, then 6, 9, 12, all the way to n. How many numbers? That is multiplication of n, also n over 3. Okay, n over 3. Well, it starts all, and when j finally reaches to be n, then I print 1 star. J will be first 1 and then n, or will be n immediately. So how many stars do I print altogether? N plus n half plus n over 3 plus n over 4 plus. This is not a geometric sum. Geometric sum we'll see a lot of times in this course, many, many times. But this is not one. Geometric sum will be when it's n plus n half plus n over 4, n over 8, n over 16. This is not, that has a name, 1 plus half plus third plus quarter plus all the way up to 1 over n. That's a harmonic sum, and it is equals to n ln n plus tiny little noise that we can ignore for this practice. If you know calculus, it should remind you what this summation should remind you the integral of 1 over x dx when x starts from 1 till n. Right? What is the area of this function? What is the total area when I start at 1 goes to n and ask what is the area of this function, and this is ln n. How is this related to the sum? Well, the sum is like numerical evaluation of this integral. If you know what are integrals, great. If not, just remember that this sum has a name. It's a harmonic sum, and it equals to n ln n, ln log to the base e of n. Questions?
So will it be O of n ln n or theta?
It's theta of order of n log n,
Okay.
or n ln n, both are legit.
Okay.
But actually I want to be a bit more uptight about it. It's exactly, the number of stars is exactly n ln n,
Okay.
plus minus 1. Okay, I have some number a. A is anything which happens to be half, but it can be anything as long as it's smaller than 1. A is any constant smaller than 1. Print n stars, print n star, and now do n equal a times n. If a is half, then replace n by half n. If a is 90%, then n now is 90% out of its previous value. So my house worth $100,000, and the next year my house lost 10%, so I need to multiply its value by 0.9. Next year I need to multiply the new value, which was 90% of 100 times 90%, because it lost again 10%, and so on. And we keep doing it as long as n is larger than 1. How many stars do I print? Well, in the first iteration, I printed n such star. J goes from 1 to n, print n stars. Second iteration, well, at the end of the first iteration, I set n to be a times n. A was 0.5, then I halved n, or multiplied by 90% or whatever. So now the number of stars that will be printed in the next iteration is a times n. Say 90% of. Next iteration of the y, I'm using the previous n, which was this one, except that I multiplied it by a once again, so it's a squared times n. 90% times 90% of the value of the house. Third iteration, 90% of 90% of 90%, a cubed times n, and so on, and let's even this sum continue until at some point, at some value t, that some of you, I'm sure, no matter how much I told you that you can avoid it, some of you will still insist of computing it exactly, even if I don't ask, but take my word. You can definitely cut some corners here. At some point, this sum ends when a to the power of t becomes, times n becomes less than 1. So writing this sum again, it's n times 1 plus a plus dot 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 all the way up to a to the t, which is in terms smaller than n times, I copied everything here, so all the way up to a to the t, and then I'll add a to the t plus 1, a to the t plus 2, a to the t, all the way to infinity. That's why this is why this is strictly smaller than this. Here the 3 dots means I'm going all the way to infinity. Why did I do this trick of adding elements? Well, because I wanted not to care about what is t, but just let it go to infinity, because it doesn't matter much to the running time. It matters less than 1 unit to the running time. All in all, this is just the geometric sum, and the formulas that tell us what this is this equals, when a is smaller than 1, this equals to 1 over 1 minus a. If a was half, then it's just what you have here, n times 1 minus half, making it half, and divided by it, making it 2n. Okay, so, and we'll see it again, this type of summations. Okay, properties of big O's. If I'll ask you to prove it formally, here the proof. Formally, you need to pick to tell me that if I add T1, if T1 and T2 are both order of 2 other functions, the moment that I made this declaration, it means that I can show you, if you'll ask. I don't want to be very tedious, I will not show you this constant if you don't need details. But if you can, if I make this claim, it means I can show you constant n1 and c1 such that p of n is smaller than c times g of n, for which n? Only for large n, n larger than n1. The same goes for the other function, t2. I can show you such constant, n2 and c2. How can I prove to you that t1 plus t2 is order of g1 plus g2, besides that it's obvious? Well, I need to show you constant. Legally, I can be dragged to court and then they'll ask me, show us a real constant. Well, what are their values? Which value will I use? I'll say that for if this is true, it means that there is some constant n that tells you only, my claim is true only for n larger than what? I'll take for any value that is of n which is smaller than both n1 and n2, any value of n that is larger, sorry, for both n1 and n2. How can I make sure that larger than both N1 and N2, and say N is larger than the maximum of the two. Which constants will I use for inside the big O? Lots of options. I can use just constant C, which is C1 and C2. Where did I get these values C1, C2, N1, N2 from? Well, I just told you that this is true, so I must have shown you this constant. So if this is true, then I can generate these constant, and from this it's pretty obvious what's going next. And not very fascinating. Like, we're not making a course about proving big O notation. Okay, so if T of 1 is order of n squared, you have one function that runs in order of n squared, and T of 2 is n log n. For example, you have a code that runs in n squared steps, and in every such step you are calling another function that runs in n log n. What would be the overall running time? It's just a product of n squared and n log n. Left with just the product. You need to prove, of course, that if T of 1 is order of G of 1, T of 2 is order of G of 2, then when you multiply, then you're getting something that is order of G1 times G2. And in the homework, I ask you if it's true that if T of 1 is order of G1, T of 2 is order of G2, true or false, the T of 1 of n, of course, I'm just lazy to write, T of 1 to the power of T of 2 of n is this order of G of 1 times to the power of G of 2. Because we know that when we multiply it works, we know that when we sum them it works, well, it works also when I write them in the exponent. It's very tempting to say yes, but the answer is no. Just take a T1 of n to be 3, which is order of 2, T2 of n, which would be n, which is order of n, and it's not true that 3 to the power of n is not order of 2 to the power of n. There is no constant that correlates these two. Okay, so that was the case of no. There is much nastier, more nasty question in the homework that asks about a sequence of functions, and that's I'll tell you the trick. The answer is no, but I'll tell you the hint. The answer is no for the sequence of functions, but you have to show why it's not. It's again one of these things that it's obvious, and the proof of is how can it be any other thing, but it's still not true. Okay, let's talk slightly about divide and conquer. How does QuickSort works? I'll skim many of the details that I asked you guys to go. Everybody's on Piazza by now, I hope. If not, please register. And in Piazza, I ask you to go over these details, how QuickSort works as a code. You can write it in many variants. What you want to do to have from QuickSort basically is you pick a pivot X, divide all the elements into the left side of elements that are, it's actually a typo, should be strictly smaller than X, and the other side of elements that are larger or equal than X. You will need to break the symmetry somehow. About where are the elements that are smaller or equal than X. And once you have such a partition, there is plenty of things that we can do with this. For example, QuickSort, for example, computing the median in linear time. Another exercise for today. Okay, and that can write slow or fast, depending. The partition itself takes linear time. That's the code that appeared in CLRS. I have mixed feelings about it. It's somehow less intuitive, but to me. But you can move from one pointer from the left of the array until you run into an element that is too large from the pivot. You can write with a pointer from the right side of the integer you run for an element that is smaller than the pivot. That by itself is not necessarily something that indicates a violation, but if the left pointer is to the left of the right pointer, like so, then obviously I need to replace it. Again, the big X here indicates larger than the pivot, small x indicates smaller than the pivot, and then you need to replace it. And when you implement it the first time, you almost always run into issues about what happens if my array is of size 1 and some problems. So it takes a bit moment to make it bugs free and run with all the safety tests. The code from the book just runs from one pointer that is seeking small elements, another pointer that seeks for large elements, and once I need to replace them and keep on going. So the invariant will be that all the small elements would be on the left side up to I, all the large elements will be up to J, and what happened after J I have no idea. So J will go larger and larger. Okay, and the running time is obviously linear, nothing much to say about it. Why it's linear, moving with a pointer and go up, and please check it by yourself in the textbook or the slide. Okay, QuickSort in general, how do I use the partition? And QuickSort will not be the only algorithm that will use a partition. One of them, what do? I give an array A, and I want to sort everything in the array A all the way from P, the left side, to R, the right side. There are two indices. If P is smaller than R, what do I mean? If P equals R, then my array just contains one element and there is nothing to do. If P is actually larger than R, then there is some error. Could be, it's not necessarily a reason to crash, but my code might produce it. So, but either way, there is nothing to do. So only if my array contains at least two elements, what do? I pick a pivot, I perform a partition of the array from P to R, and I'll also run the partition, what you've seen in this previous slide. The partition returns for me where is a pivot such that this is R, where I keep the pivot. All the elements from here are smaller than X. That is, all the elements from P, I'm blank, Q, Q is a value that the partition returns. That's where the pivot is going to sit, at index Q of the array. The left side from P to Q are all smaller than X. The right side from Q plus 1 all the way to R are elements that are large or equal than X. Why don't I just call them 1 and n? Well, because I'll call them 1 and n when I call the array the first time, but the recursive calls will work on smaller and smaller subarrays. People, any questions so far? All good? Okay, what's the running time of a QuickSort? All depending on how lucky we are on picking the pivot over here. How good is X over there? Worst case, what happened in the worst case? Somebody sorted the array for us and we don't know it. And we always use the very first element, the first element in the array as a pivot. Okay, bad idea. What will be the running time in this case? T of n, running time of n elements would be you're spending some constant to initialize a function. You're performing partition that takes theta of n. If you're not familiar still with theta, no less than n, no more than n, constant times n. That's just to do the partition, even though the partition, because your algorithm is completely oblivious to the fact that x that you picked is the smallest element. So what would be the result of the partition in this case? That you start when x, which is the smallest element in the area, happened to be in the first one. After the partition, x still is here. And you just don't need to start calling the array from 2 to n instead of from 1 to n. Now you need to partition only the right side. So how many elements on the right side? All you got is moved down from n to n minus 1. Invested a lot of time, get very little effort. What is a recursive? What is a solution to this recursive formula? That we already had in one of the examples that I showed you, that here I printed n stars and called myself with n minus 1. It's exactly the same behavior, which is just arithmetic sum. 1 plus 2 plus 3 plus all the way to n, making it theta of n minus 1. It's a great example to show you a quick and dirty techniques that I really like. How do I know? You all forgot that there are formula for arithmetic sum. At this moment, I showed you the red light, and you look at it, and you just forgot everything that you know about arithmetic sum. The scenario right now is that I don't see the remote of the overhead. I get signal from the overhead camera to the OBS, but it's frozen, so it didn't change in the last half an hour. So I'm happy that at least I brought this webcam that can give us recording of something. So I want to give you a quick and dirty case to prove lower bound. It will be nice, but not that's useful. It will be nice when you don't remember what is a arithmetic sum, but there are cases that I don't know any other proof beside it, and that works very well. I'll show you two examples. The first would be quite simple. So let me read to you what I just write. I want to prove that 1 plus 2 plus 3 plus all the way up to n, that this is theta of n squared. Well, you all know that it's order of n squared. That's easy because each one of these elements is no larger than n, and there are n such elements, so it's no more than n squared. But why is it also omega of n squared? Remember, you just all collectively forgot arithmetic sum, so you don't know what this formula actually summing up. Now, what I did along this way is I highlighted that between 1 and 2 and all the way up to n, somewhere here there is an element n half. And after this element n half comes n half. Let's say that n is even, keeping it simple. N is even, so n half is integer. Here is n half, here is n half plus 1, here is n half plus 2, all the way to n. Look at all these red elements. Starting from n half all the way to n. How many elements do I have here? Just big elements, just elements that are larger than n half. How many do I have? Yeah. How many do I have? N half, maybe plus minus 1 if you want to. Well, everybody agrees? I just count the elements that are actually larger than n half. And in this very toy problem, there is exactly n half many such elements. What is the value of each one of them? Well, at least each is at least n half. So the sum is large or equal, then how many elements do I have? N half such large elements. Each one is n half or larger. So if I take this guy, n half plus 2, and push it down to be just n half, I decrease the sum, right? That's why this is larger than this, large, strictly larger. Okay, so n half times n half, making it n squared over 4, making it omega of n squared. Okay, we can do it. Works even if what you're getting doesn't have a real nice formula. Everybody understood? I'm inserting n keys into a tree, and my tree to start with is empty. Now, it's a balanced search tree, so in a balanced search tree, hopefully all of you know at least one type, AVL tree, red black, 2-3, red neck, a skip list, maybe not exactly a tree, but still works. All of them all gives logarithmic time per operation. So what is the overall time? Time is order of log of, but let's ignore the order. So just write the log itself. It's log of 1, because I just inserted element into a tree that is empty, plus log of 2, plus log of 3, plus log of n, all the way. What's the overall running time into it?
Well, the logarithms will compress to be n factorial, log of n factorial.
Which is?
Something.
It's log of n factorial, which you, if you know about Stirling formula, you can get some exact expression, and you can you can get pretty close to the exact value, but we are still in the quick and dirty tricks. So, everybody understand why I got to this summation, log 1 plus log 2 plus log 3 plus all the way? Because when I'm inserting the third element, it takes me log of n at this moment. There are only 3 elements in the tree. 4 elements in the tree all the way up to n minus 1 elements in the tree all the way to the last one. There is a constant before all of them, but it's the same constant, so I don't care. So each operation, each is order of log n, so total is order n log n. Order, remember, no more than log n. There's an upper bound. That's legit. But is this tight, or can I come up with a better lower bound? So I want to show you that it's actually also omega of n log n. And in this case, I don't know any way without the dirty trick. How can I prove that it's also omega of n log n? Let me show you. I'll write this sum again. Log of 1 plus log of 2 plus dot 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 log of n half. Again, I'll assume n half is even, plus log of n half plus 1 plus log of n half plus 2 plus dot 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 log n. See where I'm going with this? I just highlighted somewhere the element in the middle. Sorry for the camera doesn't get recorded. Log, as you know, is monotonic function. The larger n, the larger the log. So this number is large or equal . Look at these weird elements. Log of n half, log of n half plus 1, log of n half plus 2, all the way up to log n. They are the large elements. This is larger or equal than log of n half plus log of n half plus 1 plus dot 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 log of n. I just deleted a bunch of positive elements, so I made the whole sum smaller. But this is larger than this because all the non-red elements are not copied over here. And they're all positive. And this is in turn larger or equal than, here I have log n, and I'll write log of n half, and I'll write log of n half once again. What should I write here instead of the next element? Smaller. Sorry?
Log of n over 2.
Log of
N over 2.
n over 2
That's right.
once again. But instead of log of n plus 1, because I want simple formula, I just write log of n without a plus 1. Because of the function of the log, this is larger than this. Plus log of n half plus dot dot log of n half. The last element, camera doesn't see it. I hope to get sponsorship from Monster. All good? Just I pushed all the elements to be in the lowest common denominator, if you wish. How many elements? Each one is now smaller than what it was before the pushing down. Each one is log of n half, nice and friendly number. How many of them do I have? I have exactly n half many such elements. I just care for the smaller one. So this is larger or equal than n half log of n half which is omega constant times n log n. And that's the case that I don't know any other formula. So what do we know about the sum of log 1 plus log 2 plus dot 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 log n? It's not more than n log n, and it's not less than n half times log of n half. But as far as constant is concerned, both n half and n and n half are different just by a constant. So the overall running time of this algorithm is theta of n log n. What's the base of the log? I don't know, I don't care. Base of the log don't affect the constant. Okay. Back to our QuickSort. So QuickSort, despite the name, can be very slow. Is this clear? I'm happy to repeat if. Okay. Okay. Everybody sees why it is n squared in the worst case. And one of the way to improve the expected running time is to say I pick a random value k, which is an index between p and q, some integer between p and q, and my pivot would be a k. AK is this value that I just picked, that's my pivot. That is, whom do I pick as a pivot? Not necessarily the first element, not necessarily the last one, a random element in the pivot. A random element in the array. Okay. Now, what happens if I am very lucky and the element that I pick is always the median of the array? Let's assume that yeah.
The array always splits in half.
The array always splits at half. I always pick the median. So the overall running time follows this recursion formula. By the way, if you don't like recursion formula, we're in the same boat. I'll use the recursion formula that we need in other parts of the course. I don't see much prettiness or coolness in it. This is one of the cases where you just see it lots of time through the course. Let's see what's written here. T of n is what? Theta of n plus 2 times t of n half. Why? I took the array, I performed the partition, pivot x is exactly at the n half element, and now I sort recursively the left side. There are n half many elements there, and sort recursively the right side. There are n many elements here. Now, since I didn't like recursion formulas, well, we can solve it by looking at the recursion tree, which you have seen. I looked for something that you can generalize for other cases and be more useful. So let's ask, if we are always picking the median as a pivot, how much work does the algorithm take? Let's think about some number, a over here. A is one of the keys that sits here in the array. At some point, A is compared to a pivot, N is copied to a different array. So I copied A into a new array, but in this new array, the size is n half. And I spent constant time to move A from this array to this one, small a. And then I copied another unit to copy A again from here to an even smaller array of size n over 4 and so on. How much work did I spend per this one key A? Log n. Each time its array is halved. So the work that I spent for one key is log n. Overall running time, n log n. But that's much, I think, more intuitive proof. But picking the median is not fun. Picking the exact median is not fun. I'll actually teach you how to use it, but and one way to find the median is to sort the array. Another one is to use randomized algorithms that I'm going to teach you. Another one is to use deterministic algorithm with a horrendous running time and not fun to implement. Even though it's in the worst case, it's order n, but that's a case that the constants make it completely practical. What should we do instead? Let's ask what happens if the pivot that I pick is a good pivot. And let me define what is a good pivot. Good pivot is an array that is not one of the smallest 10%. I do it like the left side of the array, but it's misleading. The array is not sorted. Small elements are completely messed up with the large elements, but think about the smallest 10% of the elements. If I would have got the array sorted, then the 10% of the elements over here. And these will be the 10% of the big elements. Let's call a pivot a good pivot if it is not in the largest 10% and it's not in the smallest 10%. So it's kind of comparison. The best is if I'm exactly in the middle. The worst is if I'm exactly at the end or exactly at the beginning. What happens if I'm in this 80% in the middle? Well, it means that then when I split the array, the portion of the array would be that on the left side, I have at least 10% of the elements on the left side, maybe more. And on the right side, I'll have at least 90%. Actually, the lowest that I can have here will be smallest 10%, and again, the theta of n, which is a recursion, which is just the time for the partition. So that's linear no matter what, doesn't depend on what it is. What the running time, again, didn't like the recursion tree, so follow the book for the recursion tree. If you prefer my proof, then let's follow it. A over here used to be in an array of size n, but I picked a good pivot, then next the array that contains A is not n half. Maybe it's n half, but how small can the array that contains A now be? It's, since I only used good pivot, this array is larger or equal than 0.9, at least 90% of A. I take it back. It's somewhere between the array that the size of this array of A, or the worst example of the running time would be if the new array of A is indeed 0.9 n. It could be, if it's smaller, it's better for me, because what I'm going to ask for this small element A is how long does it take before A finds itself in an array of size 1. If I don't find good pivots, this array can be linear size, n minus 1. Here I find good pivot, so this array, in the worst case, lost at least 10% of its value, so it's actually a small or equal. Sorry about it again. The size of this array is no larger than 90% of n, because at least 10% went to the other side. Call this array once again. The size of this array, it lost at least 10%, so it's 90% of 90%. We saw this loop again, this sequence already today. Next, it would be 90 times 90 times 90 times 90, 0.9 to the k times n. How large can k be until, how large can k be until 0.9 to the k times n? How large can k be such that 0.9 to the power k times n starts to be smaller or equal than 1. Play with it a bit. It is log, but not log of 2 of n. It's log to the power of 1.1. Where did it come from? Look at 90%, it's 10 over 9. Well, you look at the inverse. Which is what? It's like log 2 of n divided by log 2 of 1.1, which is 8 times log 2 of n. What did I get from it? That the overall running time is therefore 8 times, if all I pick are good pivots, kind of unlikely, but if miraculously all I pick are good pivots, not in the smallest, not in the largest 10%, then the overall running time for one element is 8 times log n, and for the overall algorithm is 8 times n log n. Okay, but how can I guarantee that all I pick are good pivots? How can I guarantee that all I pick are good pivots? Well, I missed the slide here. Then I prepared the new slide today. So picking a good pivot, well, first, if I just pick one random key, what's the chance that it's a good pivot? Not very hard question.
80%.
80%, it's not in the smallest and not in the largest. If I want to enlarge it, I'll pick 5 random and take the median. Let's see what's the probability if I pick 3. Let's do 3 elements. What's the chance that if I pick 3 random variables that the median is in the smallest 10% or in the largest 10%? Let's do this math. I pick 3 values at random. What's the probability that the median is in the smallest 10% of the array?
You either have to pick 2 of the lowest and possibly 3 of the lowest. 3 of the highest.
So an obvious and wrong answer would be to have the median be in the lowest, the whole 3 needs to be in the lowest. That's one case. So one case is all 3 and this happens with probability of 1 over 10 to the power 3. Not very likely. But that's not the only case. Now, let's pick A, nothing to be with A, then B, then C, and it could be that A is in the smallest, B is in the smallest, and C is not in the smallest. A in the smallest, B in the smallest, and C not in the smallest, not necessarily in the largest, not anywhere inside the smallest. That here again the median will be in the smallest 10%, and the probability of the first 2 in smallest and the last not in smallest, the first 2 in the order that I pick. This would be 1 over 10 times 1 over 10 times, and the last one is not in the smallest, so it's 9 over 10. That if the order is given, just the first 2 order. There is another case that I need to think about, that the first is in the smallest, second not in the smallest, third in the smallest. Probability is the same, but it's a different event. And another event is that it's not in the smallest, and the two next are in the smallest. So in short, I need to multiply this number by 3 plus this number. All in all, you're getting about 3–4% that the element that you pick is a bad pivot. But it's the bad pivot in the smallest, and you have the same probability that it's in the largest. Everybody understood? Once again, I have a few cases, and I want to divide them into disjoint cases so not to double count the probability. So one case is all 3 elements are in the smallest 10%. I ignore the largest. Another case is the first 2 are in the smallest, and the third one is not in the smallest, otherwise I would double count one such event. The other one is in the larger 90%. I don't care if it's in the largest 10% or not. Okay. First 2 in the smallest, what the probability is 1/10 times 1/10, because it's more than 10%, 1/100, times 1.9, because the last one is outer. But that's when the order is given. I told you which one of the 3 in the order are in the smallest, the first 2. Now I need to multiply this number by 3 because it's possible there is another event. You hit the smaller, you hit red, blue, red. That's another event that has the same probability of what it is, 9/1000. And you have another event of red, blue, red, with another event which has the same probability. So that's why 3 times 9/1000, make the calculation, it's a few percent, plus 1/1000. And if you want to even make it a bit smaller, then pick 5 random instead of 3 random. Yeah?
Why is it multiplied by 3? Shouldn't it be multiplied by 2, but both of them are multiplied?
Well, I said one, I'm not committing that that's the simplest way to solve it, but a way to solve it is to say, I picked the first one, the second one, and the third, in this order.
Oh, okay. Gotcha.
And it could be that the first one that I pick is in the red, second one in the red, and the third one in the blue. What's the chance that this happens? First one in the red, 1/10. Second one in the red, 1/10. Third one in the blue, 9/10. Okay, meaning that we have, even if we pick 3 random elements and pick the median, we already have a great chance that QuickSort will run in n log n. But hey, it doesn't say that QuickSort always runs in n log n, but what does it say? That you have about, let's call it 5% chance that I pick a bad pivot, 5% chance that I pick a bad pivot. What's the worst, what is the impact of it? That I did a partition that didn't harm me, just take some time without really get any effect about really splitting the array significantly. So out of every 5% of the work is redundant. You did partitions that are not significantly helpful, maybe even multiply the useful work, but on every, but for every one redundant time that you run the algorithm with this bad pivot, you also have a running time that is a good pivot. But still in the level of hand waving, where we are going is to use random variables, expectation, and then we'll see exactly what is the running time of QuickSort, and that will be the harmonic sum n ln n once again. But I want to play a bit with random variables. So we talked about it last meeting. I'm tossing a coin, and it is on a falls on face or tail. And I'll say that if the coin is fall on face, assign a random variable, and once again, random variable. For me, it's a function that looks at what are the result of the coin and assign to it a numerical value. And how do I assign this numerical value is up to me, but we will see that most of the time it's convenient to think about 0 and 1. but there is no correct, incorrect of how do you assign these values. So now if I decide that x is one of these functions, a random variable, and x is set so that if the coin falls on face, then x is 1, and if the coin falls on tail, then x is 0. I can define a different function, y, which is 5 if the coin is on face, and y equal -3 if it's tail. Maybe then I'm earning $5 or need to pay $3. Now, once I told you that the coin is legit and fair, and I told you what is my random variable, I can ask what is the probability that x is 1. Well, x is 1 happens if and only if the coin is on face, which if the coin is fair should be 50%. What is the probability that x is 2? 0, because it never happens. I didn't assign any value to it. Okay, and similarly, I can ask what the probability is that y equals -3, that I need to pay $3. Coin is fair, 0.5. Okay, this is similarly for a dice. I roll a dice. I see the number 1, 2, 3, 4, 5, 6. And I can define a random variable f, which is 1 if the dice shows an even number. So f is 1 if the dice falls on 0 number, and if 0 if it is on 1 or 3 or 5. Q, yet another random variable that results by the dice, and I can ask once again, what is the probability that f is 1, which happens if the dice falls on an even number, which is 0.5 once again. What is the probability that q is 1? Well, q was defined as the dice shows a number that is larger than 2. So if q is 1 if the dice shows a number that is 2, 3, 4, 5, 6, the probability that this happens is 5/6. Okay, everybody feel convenient with this notation? The probability that this event happens. If it's the first time that you say it, you probably don't feel comfortable, but please please get used to it. Now I can ask what is the expected value of y. Expected value of y is the sum, we had it last meeting, all the j of all the values of j that I need to consider. If j is integers, and it's only integers, maybe minus infinity to infinity, depending on what it can be, of j times the probability that y equals this j. Again, the intuition is what is the expected value that you see. If you're doing it billion times, what is the portion of times that the dice will show you j as a result. And now I can ask what is the expected value of y in this case, and even though this sum is infinite, the probability of almost all the events are 0. So the expected value is 1 times probability. If I get $1, probability of 6, $2, probability of 6, $3, ... times $7, but the probabilities that I see on the dice 7, which I never see, so this is 0. So it's 1 plus 2 plus 3 all the way 21 divided by 6, which hopefully is this number. That's the expected value. Okay, let's play with Let's play with this example. M equals 0, and M is going to keep the maximum that I've seen so far. Again, M is going to pick the largest number that I've seen so far, and counter will keep track of how many times M was changed. Now for I goes from 1 until some number n, Si is a random value between 0 and 1. And we can have random written in different ways. The random here means pick a value between 0 and 1 uniformly. Each number, every float between 0 and 1 has the same chance to be picked. And if it is larger than the maximum that I've seen so far, if it's larger than the maximum that I've seen so far, then I'll change M to be Si, to be the new maximum. If Si is larger than the maximum that I've seen so far, then I'll set M to be Si, and I'll say the number of times that M was changed have been incremented by 1. Okay, at the end, of course, I know what is M, and I'm asking what is a minimum number of times, what is the minimum value that I can see of CTR, of the counter. Could be 0 or 1. If you think that it could be that the minimum that the Si could actually be 0 by itself, maybe I don't change it at all, maybe I change it once. But as long as the first number that you see, Si, is larger than everybody that you'll see after that, you will not change the counter at all. But so the minimum of M, so CTR will be maybe 0 or 1, something like this, as the minimum number, mean value of CTR. What would be the maximum value, which would be actually not less unlikely?
So that would be every time you have to change it?
Every time that you pick a new number, it was larger than the previous one, which could be the max, could be n. Not very likely, but could be. Each number was larger than the previous one. Okay, I apologize for the camera. And what I want to ask is, what is the expected value of CTR? And to do it, I'll define a random var. I'm actually going to define n random vars, x1, x2, xn, where xi is 1 if si is larger than if si was updated, if m was updated at the ith stage, that is when I picked si. xi is 1 if when I picked si I changed m, if xi is 0 otherwise. So as most variables that we'll see, it will be a Boolean variable. 30 more seconds, and I'll set you free. Let's say that I'll start when m starts to be -1 at the beginning, so I'm sure. What is the probability that x1 is 1 if m start to be -1? What the probability is that the first value that I pick is larger than m? 100%. I definitely change it. So the probability that x1 was 1 is 100%. That's easy. What's the probability that the second number that I pick is larger than the first number that I pick? Well, one way to think about it, it's conditional probability depending on distribution area. That's a complicated and unneeded. We are in this course about quick and easy tricks. I picked the first number, I picked the second one. The way that I pick the second one doesn't affect any way how I pick the first and vice versa. So I picked two numbers in no particular order. What's the probability that the second one is larger than the first? Exactly the same probability that the second is smaller than the first. Completely symmetric. So the probability that x2 equal 1 is half. 50% chance that the first is larger than second, and 50%. Here is where it starts to be slightly more interesting. What is the probability that x3 is 1? The third time that I change the maximum. Just because of time, I would like to. So let's think about it. I picked three numbers, and then maybe I decided about the order. It's not exactly what I did. I picked three different numbers, but you can think about them as I picked three numbers, and then I decided about the order between them. There are 6 permutations, whatever. Out of the three numbers, there is the largest one. I picked three numbers. Out of the three, there is the largest one. Ignore the case that the same value appears twice. Out of the three, there is a unique largest one. What the probability is that it was picked in the third step? The same probability that it was picked in the second, same probability that it was picked in the first. Out of the three, there is the largest one, and it's exactly the same probability that it appeared as a second, or as a first, or as a third. So this is just same? 1 over 3. And for xi, we'll repeat it. Next meeting, for xi, it will be 1 over I. And when I'll sum up all this expectation, I will get, how many times do I change the maximum? Log, be a bit more precise. Ln of n, because it will be the harmonic sum. 1 plus half plus 1 over 3 plus dot 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 1 over n is ln n. That's why I showed it to you in details earlier. And that's the expected number of times that the maximum is changed. See you Tuesday.
Yeah, I know.
Yeah, you got it.